Okay, so today we're going to try to prove that any convergent sequence is Cauchy, and that a Cauchy sequence of real numbers converges to a real number. So for the first part, we have a convergent sequence AI, which converges to a number A. Right. And by definition of a convergent sequence, we have that for all epsilon greater than 0, there exists an n, so that for all I greater than n, AI minus A can be made less than epsilon. Thus, we can choose a term in the sequence such that for all terms greater than that term, the difference between it and the value the sequence converges to can be made arbitrarily small. More, for all I and j greater than n, we have by the triangle inequality that AI minus AJ is less than AI minus A plus A minus AJ. And since we can make each of these individual terms as small as we want, we might as well make them less than epsilon over 2. And since we made these less than epsilon 2, this term can be made less than epsilon. And that is precisely what it means to be a Cauchy sequence. That is, for all epsilon you can give me, for all epsilon greater than 0, I can choose an n so large that for I and j greater than n, I can make this difference arbitrarily small. And we just showed that, given that we have a convergent sequence. Now for the second part, that a Cauchy sequence of real numbers converges to a real number. So first I'll give you an example of a sequence of rational numbers that converges to an irrational number. 4 minus 4 over 3, 4 minus 4 over 3 plus 4 over 5, and so on. And this converges to pi. So we have a sequence of rational numbers that end up converging to an irrational number pi. Right. Now for the second part. So we have a Cauchy sequence of real numbers. So we choose any n, and we define n equals n plus 1. Right? And for all numbers, for all m greater than n, so for am, we have am is in the compact set where an minus epsilon and an plus epsilon. And what this is just a reiteration of the definition of what it means to be a Cauchy sequence. That for we choose any n, and for all m greater than that n, am lies within epsilon of an, and that's just what it means to be Cauchy. That am is within epsilon of an, and I just made this explicit by making a compact set. So am is between these two values, and because this is a compact set, we can apply the Bolzano-Weierstrass theorem, and which says that exists at least one subsequence that converges to A. And if every subsequence converges to A, then the Cauchy sequence converges to A. But let's suppose for contradiction that there exists another subsequence, that converges to B. And since A and B do not equal each other, we'll call their difference epsilon prime. Actually, we'll call their difference divided by 3 epsilon prime. Now, we go on and apply the triangle inequality again. Right? And we can set this equal to A minus an plus an minus am plus am minus b. Now we can choose an n so great that for all n greater than this n, the difference between an and a can be made less than epsilon prime. And again, that's taking advantage of what it means to be Cauchy. And here we can do the same thing. We can choose an m so large so that am is within epsilon prime of b. And by how we've constructed a minus b, up here, this is just 3 epsilon prime. by just multiplying both sides by 3. Alright, oh sorry, this is less than or equal to. So, and if this were to hold true, if this we know that this is to be true. If this were to hold true, given that there exists another convergent value, then this must be greater than epsilon prime, the middle term. And if the middle term is greater than epsilon prime, then we've contradicted ourselves. This is greater than epsilon prime, then an minus am is indicative of a non-Cauchy sequence, and that's a contradiction because we originally assumed that the sequence was Cauchy, and so we can conclude that a Cauchy sequence of real numbers converges to a real number, and we've completed the proof.